let me point you out here. In our discussion last, was that Friday, I guess it was, we were talking about drinking too much, right, and some of the effects of that. Jordan found this very solid video that I put up on the Schoology, and I would highly encourage you to check it out. I think it will help you with this next section, with chapter 18's piece about how we maintain water and electrolyte balance, because it uses a case study. It's using the study of, we talked a little bit about this, about a lady who was in a contest, hold your wee for a wee. That's like really what it was called, right? So like she had to drink 3 gallons of water as fast as you could, and then the first person or the last person not to go to the bathroom or throw up wins a wee. Okay? Which sounds like a great plan, except that, you know, she almost died. And they'll talk about why that is the case. Again, I encourage you to check it out, because what she did was basically dump a whole bunch of fluid into her system and wouldn't let anything come out. And what did that do to the cells? How did they have to combat that? Again, check it out. I think it's well worth your, what, 6 minutes, 7 minutes? I can't remember how long it was. Not very long, but well worth the conversation. So, we're dealing with water and electrolyte and acid-base balance today. And it's going to be a fairly quick run through this section, because what I've asked you in your study guides to be comfortable with, if I put it up here for you, is basically, why is it important that we maintain these pieces? And then, how do we maintain those pieces, right? How do we keep water coming in and going out? How do we keep the electrolyte balance coming in and going out? How do we maintain our acid-base balance when the buffer systems that are in our body to do that? Excuse me. And I think that we'll be fairly able to get through these pieces today. It's not superbly complicated. It's just understanding the different inputs and outputs and how those work together. Question? I'm sorry? Friday. Over what we did as well as this piece today. All together. Yep, those pieces are all together. That's why it's one study guide for urinary system and body balances. Yep. Okay, so let's jump into chapter 18 here. The first bit, well, let's define some of our terms here. Are you comfortable that if we want things to be in balance, the amount coming in has to be equal to the amount coming out? Are we cool? And we're dealing with both fluids, like water, as well as electrolytes, which the definition they are giving is molecules that release ions in water. Now in chemistry we use a different definition, right? An electrolyte is something that allows the conduction of electricity, right? But we're not conducting much electricity in our bodies, or at least hopefully not, unless you're putting your finger into wall sockets. So they're using that definition. Molecules that release ions. So give me some quick hits, like what are electrolytes in our bodies? What kind of electrolytes are we talking about? Sodium is a good one. Potassium is another great one. Calcium is another good one. And hydrogen. Those are kind of our 3 big ones. You can put phosphorus in there as well. So anything that alters the concentrations of those electrolytes will also alter the concentration of the water. And that's what I think was so good about the video that Jordan shared, was that all she was doing was taking in bunches of water, right? But why was she almost dying? Because there wasn't enough electrolytes. Because by putting that water in, she significantly diluted the amount of electrolytes in her body. And so her cells were starting to swell, and again, she almost died because she just wanted a wee. So where are these body fluids distributed in the body? Well, they are everywhere, right? There's actually more water in a male than there is a female, which I thought was an interesting piece. And that is mostly due to the fact that females on the average, have more adipose tissue than guys do, which makes sense. They're softer. There are other places in their bodies that have more of this tissue present than we do. Again, we're not talking about much, but a little bit more. You can have too much of anything, absolutely. Oh yes, yeah, definitely. Yeah, homeostasis, right? That's what our body is really working towards. So too little or too much, bad things, definitely. So two big places where this fluid is kept: intracellular, which means in the cells, right? So that's all the water and electrolytes in the cells. And then extracellular is all the water and electrolytes that are outside the cells, in that interstitial space, in the plasma, in the blood, in your lymph. These are all extracellular fluid places. And there is also this transcellular fluid, which includes the cerebrospinal fluid, the fluids in the eyeballs, the synovial fluid in the joints. This is kind of that, it's a little bit of both. You know, it's both intra and extra. Here's a nice little picture. Here's a total body in your water. Total body water present. And this is visually so you can see where things are. How does that, what is that fluid made up of? They tell you about, again, sodium, chloride, bicarbonate, potassium, calcium, magnesium, phosphate, sulfate. These are all the ions that are present there. How do they move? Mostly through osmosis. Osmosis is the movement of what? Water. That's a key piece. I'm going to say it again and again and again. Osmosis is moving water. Okay? How do the electrolytes move? That's through this hydrostatic pressure, or simple diffusion, right? If I'm more concentrated over here and less concentrated over there, it's going to move from the more to the less, right? The electrolytes. They show you a nice little diagram that's kind of just summarizing all the pieces here of these movements. This is there on page 505 in your textbook. It looks slightly different, but it's the same diagram. That fluid is coming into and out of the plasma in the capillaries, mostly due to that hydrostatic pressure. The fluid in the interstitial fluid is going both into the cells and out of the cells, again, based upon the osmotic pressure or as well as the hydrostatic pressure. And again, this is all stuff we've talked about before. I think you all should be pretty comfortable with how these guys are moving around in here. So how do we maintain balance? How do we keep the balance? And that's really the key point behind this chapter. The three different types of balances. How we keep water balance, how we keep electrolyte balance, and how we keep the acid and base balance. So let's talk about that. Of course, what do we mean by balance? Again, equal. Input to output. Equal input to output. So, how do we take water in? Well, we drink it, I hope, on a daily basis, right? And the amount gained will depend upon how much you're drinking. As everybody takes a drink, I like it. Good. About 60% of the water you get is taken in from what you drink. The other 40%, 30% of it comes from our food that we eat, because thankfully our food is not dry, all of it. And 10% comes actually from the water of metabolism. And what do we mean by that? Well, remember back to our cellular respiration? One of the products, there were two products only that we made out of I guess three. One was ATPs, right? The other was carbon dioxide, right? That was our waste product. But then the last thing that was made was water. So these are in the amount of metabolism we're doing, we are making water. How do we get rid of, interesting. How do we regulate the amount of water that we take in? Well, thirst is the main way we do that. And what you hear folks say, and I've heard this a number of times, though there's some research that is going both ways on this, that if you're thirsty, it's almost a little too late. Like you're already a little bit dehydrated by the time you are thirsty. Now there's been some research that is saying, I'm not sure about that. The point is, you and I mostly, we don't drink enough water. Right? We need to drink more. Not 3 gallons like the lady who's holding her wee for a wee. Okay? But we do need to drink more. Yes, sir?
Isn't that like
It could be. Yeah. Yeah. I'm not sure. Again, there's in the literature recently, there was a big swing over the last, let's say, 10 or 15 years to, oh, you need to drink more. Our thirst mechanisms aren't quite sensitive enough to know when we're dehydrated. And then in the last, let's say, year and a half, 2 years, I've seen many more things. They're saying, no, are you kidding? Come on. Our thirst is pretty solid. If you're thirsty, drink. You know. But again, the point being is that we do need more water than we... How do I think is the best way? Research is showing the best way to know how much you need? The color of your urine. If your urine is staying reasonably clear, you're doing good. If it's not, you need to drink more.
We're always told to drink more, and I don't think people really end up drinking more, and it doesn't really affect anything.
So there, I think that we are just so used to being dehydrated that we don't know what it feels like to actually be hydrated. And the difference in performance. You look at some of these guys who their job is to do things with their body. I'm talking about these athletes and stuff. Hydration is so key to them. They do nothing before they are drinking. That is one of their main focuses. If they don't, they notice a decrease in performance. Almost, it's across the board. So for you and I, no, I sit around all day. I'm not, doesn't matter if I have, but I do feel a difference. The days that I drink more, it does. So I just think we're just used to it. Yeah. Okay, how do we, going back. Once I drink enough, the distension of my stomach actually expanding with the water that comes in, that shuts down that thirst reflex. So that's kind of a nice thing that these things they're regulated. I can't just keep drinking and drinking and drinking, right? Your body will say, no, I'm good. How do we get rid of water? Give me some ideals. We urinate. We sweat. What else? We breathe. Right? If you breathe on a window, it's not cold enough to do it out there, but if you breathe on a window, you'll see the water, right? What else? Sorry? Sure, yeah, you have the saliva. Absolutely. Your feces. There is also just an evaporation from our skin. It's one of the things that keeps us cool, right? So when we sweat, yes, we're producing sweat, but that evaporational piece does happen as well. Insensible perspiration. They talk about that. Okay? How do we regulate that? Well, you all already know about this, right? The nephrons regulate how much water we keep in, right? Through those distal and proximal convoluted tubes, through the nephron loop, right? If we have little bits of water, it's going to keep as much of that water out. If our body has a good amount of water in it, it'll let some of that water go through. Hence, very dark urine if you're dehydrated, very light urine if you are not.
Back to what you were saying about the breathing. Is that in the textbook you're saying that the way that the water gets the body's evaporation from water from the skin and from the lungs you're breathing, is that from the
Yes. Yeah. If you go to a window, that's the water, right? From the breath I am breathing out. Okay, and of course, you remember about antidiuretic hormone, right? From the posterior pituitary, that anti means against. A diuretic means you go to the bathroom a lot, right? So the antidiuretic hormone would stop your urination. It would slow that process, right? So if you're drinking enough water, that ADH will be inhibited, so therefore, you'll continue to use the bathroom normally. Does that make sense? In other words, if you are dehydrated, you go to the bathroom less. Again, think of those super hot days in the summer, right? When even though you're guzzling lots of water, you never have to go to the bathroom. Because again, that ADH is kicking in saying, hey, no, don't pee that out. I need that water. Keep it in. Again, nice little chart. You guys have these in your textbook too, right? Yeah, they're on top of page 508. That's just giving you visual. Here's input, here's output, here are the ways that you lose and take in. Questions there with water loss? And again, to me, I think this is one of the most straightforward chapters we've ever done. That's just, boom, it's just understanding the different pieces of coming in, coming out, and how we control that. Okay, the next piece, electrolytes. So again, balance is when the amount entering is the same as the amount exiting, right? How do we take in electrolytes? Well, we've got a couple that are very important. So we've got to have sodium, potassium, calcium, magnesium, chlorine, sulfate, phosphate, bicarbonate, and hydrogen. That's 9 different ions that we've got to have pretty consistently.
So when you drink Gatorade, you do all of it?
It has some of them. I have to look it up. I'm not sure what all is in there. Certainly lots of sodium, potassium that are in there. I don't think it has all of those pieces, though. Where do you get these electrolytes? Well, from what you eat or what you drink. Some of them will be byproducts, right? That you actually make some of these things as you break down other foods. So let's show those pieces. We'll talk about those guys. Did you know that you can actually have a craving for salt? And not like if you're pregnant. Okay? But that if your body is sensing it needs more, it will produce this craving for salt. Yeah, which is kind of neat, I thought. How do you lose electrolytes? Through sweating, in the feces, in the urine. These are the 3 main ways we get rid of electrolytes. Yes, yeah. There's only so many ways to come in and go out of our body. Yes. How do we regulate this? Well, the amount of sodium, that accounts for 90% of the positively charged ions in our extracellular fluid. And so we actually have a hormone, aldosterone, if you remember, back to endocrine system, that regulates the absorption of sodium. So too much in our blood will lower the amount of aldosterone produced. Too little will produce more to get you to absorb more. Right? All about maintaining that balance, that homeostasis. How about for potassium? Potassium is regulated by aldosterone. Again, you remember these from the endocrine system, and that is what helps us to either maintain or to secrete. And last but not least, we have calcium. And calcium, remember, has 2 different hormones that work on it. You have the parathyroid hormone, which increases the concentration of calcium, and then calcitonin, which does the reverse, right? So basically taking calcium either from the blood and putting it into the bones, or taking it from the bones and putting it back in the blood, based upon the levels that you need. And the positively charged ions are the ones that really they spend more time discussing. All of those we've talked about for the most part. Sodium, potassium, these guys are all positively charged. Any questions electrolyte-wise? Yes, ma'am. Yes. The output for each of them?
Yeah, do you want us to know about sodium, potassium, and calcium?
Yeah, I mean, the main way that they deal with that is through sweat, through urine, through feces, really for all of them, as far as output goes. I would be comfortable with how each of those pieces. Again, this is old knowledge that we have talked about in the past, so I'd be comfortable with those. Yeah, certainly. Acid-base. We'll finish it off. Acid-base balance. So, electrolytes that ionize in the water and release hydrogen ions are what we call acids. You all remember this from last year. If you're producing H's, that is an acid. If you are combining with H's, that's a base. That's called the Bromstead-Lowry definition, where you are accepting the hydrogen ions. Do you remember the other way we talked about bases? What did bases produce? OHs, good. Hydroxides. And again, the maintenance of homeostasis as far as acid and base balance depends on the control of these acids and bases in your body fluids. So how do we do that? How do we regulate that? Well, where do we get them first? And your textbook has this whole list, and I thought this was a very nice diagram that shows. Help me out, somebody. Where is this at in your textbook here? There we go. Page 511. Thank you. Nice and colorful, rather than just giving you a list. So how do we make carbonic acid? Well, that's from the carbon dioxide that we breathe in. It's one of the byproducts. How do we make lactic acid? That's from using aerobic respiration, breaking down glucose in the presence of oxygen. The byproduct is this lactic acid. Again, think of in your muscles, right? Question?
Anaerobic respiration, you said that's just breathing in.
No, anaerobic is you can still break down.
Aerobic, sorry.
Aerobic is breaking down the glucose with oxygen. That's, remember that yellow diagram that we learned all the steps of the citric acid cycle and the glycolysis? That's aerobic respiration.
That's when you make carbonic acid.
That's going to be lactic acid. This is from the carbon dioxide breaking down of glucose. Carbonic acid is one of the pieces. Carbon dioxide is a byproduct of that, right? It's one of the pieces you make, and that carbon dioxide becomes carbonic acid. When we break down fatty acids, so you all ate some fat this morning, or at least at some point today you will eat some fat, which is good. Fat's not a bad thing, remember? You need fatty acids in your diet. But as those break down, they release what are called acidic ketone bodies that, again, have this acidness to them. They produce this H-positive ions. When I break down our amino acids that contain sulfur in them, that produces sulfuric acid. When we break down the phosphoproteins and the nucleic acids in the proteins that we eat, that produces phosphoric acid. So all of these things are sources for us to get acids, H positives, hydrogen ions, in our system. And of course, you remember that not everything ionizes completely. If it ionizes only partly, that's a weak acid. If it ionizes completely, that's a strong acid. And we're just talking about how much H is produced. That's all we care about. Doesn't matter whether it's weak or strong. How much does it produce? To break apart into its ions. Let's keep rolling here. How do we regulate that? Well, we have this acid-base buffer system. If you remember buffers are things that resist pH change. So it wants to keep things at a standard pH level. And if you add acid, then it does a certain reaction to get rid of that acid. If you add bases, it does another reaction to help get rid of the bases. It's keeping your pH from changing. And there are a couple different places that we use those guys. So, and again, they can take the strong acid and convert it to a weaker one. Neutralize, right? That's our point behind these guys. So, three big ones here: the bicarbonate buffer system, the phosphate buffer system, and the protein buffer system. The point here is that we're trying to keep the pH from changing. A lot of other little conversations going on here. I want to make sure you're with me. Because remember, we have a very narrow range of pH. I may have my numbers wrong, but I want to say it's 7.2 to 7.4, which is not much, right? It's a very low range of pH. Because realize, you take in things that have very high pH and things that have very low pH all day long. You're dealing with this. And so your body works super hard to keep that pH right in a narrow range. Yes, sir?
For the regulation of hydrogen ions, do you want us to know how each system works, or do we just need to know the three systems?
We're going to talk a little bit more detail as we go here, but let me finish with this, and that may give you more what you're looking for. In the respiratory center in your brain, one of the big ways that we help control how much carbon dioxide is present, or how much acid is present, because that's carbonic acid, right, is by the rate and depth of your breathing. So if I'm exercising a lot, are you comfortable? I need lots of glucose. So I'm making lots of carbon dioxide. So therefore, the amount of carbonic acid in my blood is going to go up. Are we cool? Exercise makes more carbon dioxide. Carbon dioxide makes more carbonic acid. More carbonic acid means more acidity in the blood. We cool? So therefore, your respiratory center says, ooh, too much carbon dioxide, let's breathe more. If I increase the rate and the depth of respiration, then I'm going to expel more carbon dioxide and get more of that carbonic acid out of the blood. Remember, that was one way to transport carbonic acid from the cells to the lungs, right? Was in as this carbonic acid. So here's this nice kind of flowing of that bicarbonate buffer system, right? That's really what we're dealing with right here, is this bicarbonate buffer system.
So that's when like you just breathe more, less to change the...
Right. The rate and depth that you are breathing will help regulate how much carbon dioxide, therefore how much carbonic acid is in your bloodstream.
Basically just because that whole like carbon dioxide ends up turning into bicarbonate acid.
Right. Carbon dioxide becomes carbonic acid. Yep. Exactly. In the kidneys, how do we get rid of all this acid? Well, we urinate it out. Normally, your blood is, not your blood, your urine is just a neutral pH, right? But again, if you're eating too many acidic foods or having too much basic stuff that's in the blood, it will dump that out into the urine. This is one of the tests when you go to the doctor and they do a urinalysis. One of the things they check is they want to know what is its pH, because that can tell us if there is this acidosis or alkalosis that's going on in your body. Good. Your textbook does spend some time talking about alkalosis and acidosis. I'm not really interested in you knowing all of these pieces. Shh. I will mention them just so you understand what we're talking about. Because again, very narrow range of pH, right? So if you're below 3.75, that's acidosis. Remember, low pH means acid. If you're above 7.45, that's called alkalinosis. Alkalosis. An alkaline is a basic something. An acid is a acidic something. And they talk a bit about types of those. Respiratory, from the amount of air you're breathing and how you're breathing. And metabolic, where again you're just producing too much of this. An accumulation of acids or a loss of bases. Either way will give you this acidosis. And how do you do that? How do we compensate for that? By increasing the amount of respiration that's happening. For alkalosis, it's just the opposite. If I'm hyperventilating, I'm losing too much carbon dioxide, so therefore there's not enough in my blood, not enough acid, so therefore I have too much base. And metabolic alkalosis, I can never say that word, is if I have lost a whole lot of my H ions, my acids, maybe from vomiting, or maybe through certain drugs that are leaching those H's out of our system. So again, not interested that you don't have to know about these. I'm not going to question you on them on the test. But this is just saying, here's the final product. If I have too much or too little acid or base, here's what happens. Are you with me, my friends? Okay, I'm going to stop this here.